Hello and welcome everyone to this video lecture. So in this lecture we will talk about the theory of scaling. To be more precise, we will be talking about the Dennard scaling, and this is one of the most exciting lectures in this class EC 3030. So we will be following section 3.6 of the textbook by Marilyn Wolf. Alright, so scaling. So we have been talking about scaling in this class from the very beginning, and this is essentially an amazing feat the industry has achieved over the last 40 years. So for example, in 1970s, the device critical dimension of the transistors were of the order of 3 micron, 4 micron in the mid 1970s, and going forward, for example, now the devices are around 10 nanometer, of the order of 10 nanometer of critical dimension. So in this video lecture we will try to understand as to why we have been scaling down in the devices. So one of the things that we have said in this class is that because if we make the devices smaller, then within the same area of a microprocessor chip we can get more transistors, and if we can get more transistor we get more performance. But there is more things to it, meaning that you can get more performance, but at the same time you have certain power advantages when you scale down your devices. So that's one of the things that we'll try to understand. So the first thing that everyone talks about when they talk about scaling is the Moore's law. So the Moore's law was first stated by Gordon Moore of Intel in 1965. Now this was an observation, and the observation was that the number of transistors doubles approximately every 2 years. So that was basically an observation, and it was more it had so it was an observation basically in 1960s, and it was more of an uh, something that was stated more from an economics perspective, because if you scale down the devices you get more transistors per chip. Now this is a masterpiece. You should so this is the paper that Gordon Moore wrote, and you should definitely at least take a look at this paper that is available here, and also read the Wikipedia page. Now again, it was more of an Moore's law was an observation. Uh, so then Dennard from IBM in 1974 stated the laws of scaling based on calculation. So basically what he did was he showed that as you make the transistors smaller and also reduce the power supply voltage at the same time, at the same rate as you make the devices smaller, if you do that, then the power uh, the power that the microprocessor chip of a given area remains the same. So we'll try to understand more about it in this video lecture. And again, this was published in IEEE Journal of Solid State Circuits in 1974, and the paper is available here. You should definitely take a look at the paper, and the Wikipedia page is also very informative. All right, so let's look at what Dennard scaling is all about. So the first thing is that scaling factor X. Now, what does scaling factor X means? So it means that, say you have an nth generation of a transistor technology where the oxide thickness is Tox, the width is W, the channel length is L, the power supply voltage is VDD, and the doping of the transistor, the doping of the semiconductor is either ND or NA. The dopant density is ND, the donor density is ND for a P-type MOSFET, or the acceptor dopant density is Na for an N-type MOSFET. Now, as you go from nth generation to n plus 1th generation, then the oxide thickness is reduced to Tox over X, the width is reduced to W over X, and L is reduced over L by X. The power supply voltage is reduced to VDD over X, and the doping densities are increased by a factor of X. So if you look at a transistor, for example, in an nth generation, then the n plus 1, in the n plus 1 generation, your Tox will become Tox over X, your W will become equal to W over X, and your L, the channel length, will become L over X. So essentially your transistor will become small in all the dimensions, across all three dimensions: length, width, and the oxide thickness. And at the same time, the power supply voltage will get reduced by a factor of X, while the doping densities will increase by a factor of. Alright, so let's first look at what happens to the number of transistors as we scale down our devices. Alright, so first thing is that as we are scaling the devices, the total area of the microprocessor chip remains the same across generations. So A will remain the same. So first, in an nth generation, the width is W and the length is L. So the area of a transistor is WL. So the number of transistors in the nth generation is A over WL, and we denote it by NN. Alright, so now in the n plus 1 generation, the area of one transistor is simply W over X multiplied with L over X. So this gives us W over X squared, WL over X squared, and as a result, the number of transistors in n plus 1 generation, n plus 1 equals to A over W over L, A over WL over X squared, and which gives NN X squared. Now what it essentially means is that in the n plus 1 generation, the total number of transistors will be equal to the total number of transistors in the nth generation multiplied with X squared. Now let's say what is the typical value of X. So every 2 years, as the Moore's law said, or more realistically, almost once every 18 months, the total number of transistors doubles. This is what happens practically in scaling. So what we can say is that n plus 1 equal to 2 multiplied with nn, and that essentially means that X squared is 2, and as a result X is square root of 2, which is equal to something like 1.4. Alright, so 1 over X is approximately 0.7, and as we said, W becomes W over X and L becomes L over X. So it essentially means that every subsequent generation, both W and L gets reduced by 30%, or the area of transistors, individual transistor, goes down by 50%, every subsequent generation. Alright, so now let's look at how scaling affects different parameters of the logic gates as well as the devices. So first thing that we'll look into is the load capacitance. So load capacitance is something that we talked about when we talked about delay in an inverter and the power dissipation in an inverter, or in general in any logic gate. And the load capacitance is equal to the epsilon naught, the vacuum permittivity, multiplied with the uh, the dielectric constant of the oxide, divided by the oxide thickness, multiplied with the W and the L. Alright, so now in the n plus 1 generation, you replace W with W over X, L with L over X, and Tox with Tox over X, and what you get is CLN over X. So essentially the load capacitance decreases by a factor of X in the n plus 1 generation, right? So now the on current in the nth generation is given by this equation. So again, on current is defined as the current that flows through the device when the drain voltage and the gate voltage are both equal to VDD. All right, and here the Cox is given by epsilon naught epsilon ox over Tox. So note that this Cox n that goes into this equation is capacitance per unit area, and if you multiply it with the area of the transistor WL, then you get the load capacitance, the total capacitance. All right, so now if you go to the n plus 1 generation, you can see that this Tox is replaced by Tox over X, and as a result you will in the place of Cox n, you will get Cox n multiplied with X, then again W replaced with W over X, L replaced by L over X, and VDD replaced by VDD over X. Now VTN is also replaced with VTN over X, and the reason is that VTN, as you have seen when we are discussing MOS caps, VTN is equal to some constant multiplied with NA or ND for a p-type MOSFET over Cox n plus 2 psi b. Now if note that Na changes to Na multiplied with X. Now if Na changes, the phi b also changes, but the change in phi b is small. Now if now in the n plus 1 generation, Na is replaced by NaX and Cox is replaced by Cox n multiplied with X. Now essentially for long channel MOSFET, the VTN of the n plus 1 generation will be something that is very close to VTN over X. It is not exactly VTN over X, but for the purpose of this analysis, we can just say that the threshold voltage in n plus 1 generation will be the threshold voltage in the n generation over X. All right, so now if you do replace all the parameters like this, the on current of the n plus 1 generation is decreased by a factor of X with respect to the on current in the nth generation. So this is one of the important things. All right, so then the important metric is the delay, and the metric that Dennard used for delay is CLVDD over I on. Now why? So we used a different equation when we were talking about delay in the class. So let me just quickly explain why this is a delay. So CLVDD is basically just the amount of charge that the capacitor has, and the time it takes for the capacitor to get an amount of charge of Qn is simply the total amount of charge divided by the current that flows through, and as a result the CLVDD over I on gives an estimate of the delay of the device. All right. So now if you go to n plus 1 generation, you will just see, based on all the analysis that you have done previously for CL and ion, you will see that the delay gets reduced by a factor of x. Now in the class, what we have done is that we have shown that delay, or the rise delay, fall delay, or the rise transit time, or uh, uh, fall transit time are all proportional to RTN CLN. And we also derived an equation for this effective resistance here. Now if you use those equations and just replace all the relevant parameters in subsequent generations, you will see a similar relation for the delay. So even if you have used this equation to calculate the delay, you will see that the delay reduces by a factor of x. Now this delay getting reduced by a factor of x is a very important thing to note. So this essentially means that just by reducing WLVDD and the doping density so WLTox and VDD by a factor of x, and the doping, increasing the doping by a factor of x, the delay gets reduced by a factor of x, which essentially means that you can now increase the clock frequency by a factor of x. So again, by scaling, you have made your transistors faster. So this is an important consequence of scaling. You have made the devices faster, and as a result of the fact that the devices has become faster, means that you can now increase the clock frequency by a factor of x. So this is something that you will use while we do the power calculations in the next slide. All right, so now the power dissipated in a logic gate, as we have seen, is CL square F. So this is the power dissipated in a logic gate in the nth generation. So in the n plus 1 generation, you replace CL with CL over X, VDD with VDD over X. So, and then as we have seen previous slide, because the delay goes down by a factor of X, the frequency you can increase by a factor of X, and if you do that, you will see that the power dissipated in a logic gate now decreases by a factor of x squared. Now note that you have also increased the frequency by a factor of x. Okay. All right. So this is the power dissipated in a logic gate. All right. So now if you look at the total power dissipated in the microprocessor chip in the nth generation, the total power will be Pn multiplied with Nn. So Nn, what we have defined previously, is the number of transistors in a microprocessor. Now for this case, you can also say that okay, Nn can be something like the total number of logic gates in the device, in the microprocessor. The variation will essentially be the same. So let's use Nn prime to denote the total number of logic gates. So we'll say that it's the logic gate, total number of logic gates in the microprocessor of area A in the nth generation. Now in the n plus 1 generation, the total power dissipated will be Pn plus 1 multiplied with n plus n plus 1 dash. Again, this means the total number of logic gates and the n plus 1 generation, and this n plus 1 dash is n dash multiplied with x squared, and on the other hand, your power has total amount of power dissipated in individual logic gate has gone down by a factor of x squared, and as a result the total amount of power dissipated in a microprocessor chip in the n plus 1 generation is essentially same as the power dissipated in the microprocessor chip in the nth generation. Now note there are multiple things. Firstly, the total number of in the n plus 1 generation, the total number of logic gates or total number of transistors is higher by a factor of x squared compared to that in the nth generation, and also the frequency of the n plus 1 generation microprocessor is a factor of x higher. But even though you have increased both the number of logic gates or the devices and the operating frequency in the n plus 1 generation, the total amount of power that you will be dissipating in the n plus generation will essentially be the same as that in the nth generation, and that is the beauty of scaling. So by scaling down the devices, you have reduced the power dissipated in individual logic gates, and also you have made the devices faster, and as a result what happens is that although you have after all of these things, the total amount of power dissipated in a microprocessor chip of the same area A remains the same.